Photons from your screen travel to your eyes. They're moving at exactly 299,792,458 meters per second. Not approximately that speed. Not close to that number. Exactly that speed, down to the very last digit. This isn't just the fastest speed possible in the universe. It has a number so precise that we've literally redefined what a meter is to make sure this speed never changes, even by a single digit. Most people assume that scientists measured light speed to incredible precision and happened to get this specific number. The reality is far stranger. We decided that light speed should be exactly 299,792,458 meters per second, then redefine the meter to make this true by definition. The speed of light doesn't just happen to have this value. We've made it impossible for light speed to be anything other than this exact number. But here's what should disturb you about this fact. The speed of light isn't arbitrary. There's something fundamental about this velocity that makes it the ultimate speed limit of reality itself. This isn't just how fast light travels. It's the speed at which causality propagates through space and time. It is the speed that determines how quickly information can travel from one point in the universe to another. It's the conversion factor between space and time built into the fabric of reality. When Einstein discovered that space and time are unified into spacetime, he revealed that the speed of light is really the speed of spacetime itself. Every electromagnetic wave, every gravitational wave, every massless particle travels at exactly this speed, because it's the speed at which the universe processes information. The number 299,792,458 isn't just a measurement. It's a fundamental constant that determines how reality operates. The precision of this number reflects one of the most extraordinary achievements in human measurement. Scientists have measured the speed of light with such incredible accuracy that the uncertainty is less than 1 part in billion. We know this speed more precisely than we know the distance from Earth to the Moon, more precisely than we know the mass of a proton, more precisely than we know virtually any other physical constant. But the story becomes even more remarkable when you realize that measuring light speed required solving problems that seemed impossible for centuries. Light travels so fast that it can circle the Earth over 7 times in a single second. Early scientists who tried to measure light speed faced the challenge of timing something that moves 900 million times faster than the speed of sound. Dr. Bradley Schaefer at Louisiana State University describes the measurement of light speed as humanity's greatest experimental triumph over the limitations of human perception. The techniques developed to measure this cosmic speed led to revolutionary advances in precision measurement. Atomic clocks, laser interferometry, and quantum metrology that transformed our ability to probe the fundamental structure of reality. The number 299,792,458 contains within it the entire history of humanity's attempt to understand the nature of light, space, and time. It represents centuries of increasingly sophisticated experiments, from early astronomical observations to modern laser interferometry systems accurate to fractions of the wavelength of light itself. Tonight, we are going to explore one of the most profound numbers in all of physics, a value that connects the everyday experience of seeing light to the deepest principles governing how the universe works. We'll discover why early scientists thought light speed might be infinite, how ingenious experiments proved otherwise, and why this specific speed determines everything from the structure of atoms to the expansion of the universe. You'll learn why the speed of light has exactly this value and not some other number, how Einstein realized that this speed is really the speed of spacetime itself, and why making this number exact by definition actually reveals more about the nature of reality than measuring it ever could. We'll explore how the precision measurement of light speed led to the discovery that the meter isn't constant, but the speed of light is why GPS satellites must account for relativistic effects. caused by this cosmic speed limit, and how quantum mechanics reveals that even empty space itself respects this ultimate velocity. By the end of this journey, you will understand why 299,792,458 isn't just a number, but a fundamental property of existence that determines how cause and effect propagate through reality, why no information can travel faster than this speed, and how this cosmic speed limit creates the structure of space and time that makes physics possible. If you're fascinated by the fundamental constants that define reality, subscribe and hit the thumbs up button. And here is a question that will challenge how you think about measurement itself. If we defined light speed to be exactly 299,792,458 meters per second, what does it mean to measure something when we've made it exact by definition? Comment below with your reasoning. I'll pin the most scientifically insightful answer. The story we're about to explore connects the photons entering your eyes right now to the fundamental structure of spacetime, precision measurement to the nature of causality, and human curiosity to the deepest principles governing cosmic evolution. This number isn't just about light. It's about how the universe itself is organized. Every time light travels from any source to your eyes, it's demonstrating the fundamental speed at which reality processes information. The photons carrying this message have traveled exactly 299,792,458 meters for every second of their journey, following the most fundamental speed limit built into the architecture of existence itself. Now, let us begin our exploration of why this exact number represents one of the most profound discoveries about the nature of reality, starting with humanity's centuries-long quest to measure the unmeasurable. Chapter 1. Historical Measurements. For over 2,000 years, humanity grappled with a question that seemed impossible to answer. How fast does light travel? The problem wasn't just technological, but conceptual. Early philosophers couldn't even agree whether light had a speed at all, or whether it appeared instantaneously everywhere simultaneously. The journey to measure this cosmic constant required revolutionary thinking about the nature of observation, time, and the scale of the universe itself. Aristotle believed that light had no finite speed, that illumination appeared instantaneously throughout space when a light source was activated. This wasn't unreasonable given everyday experience. When you turn on a light switch, the room appears to be illuminated immediately. Ancient observers had no way to perceive any delay between activation of light sources and their illumination of distant objects. The first person to seriously question instantaneous light propagation was Galileo Galilei in the early 1600s. Galileo proposed an ingenious experiment. He and an assistant would stand on distant hilltops with shuttered lanterns. When Galileo opened his lantern, his assistant would immediately open his lantern upon seeing Galileo's light. By measuring the total time for this round-trip communication, Galileo hoped to detect light's travel time. The experiment failed to detect any delay, but not because light speed is infinite. Light travels so fast that even across several kilometers, the travel time is measured in microseconds, far shorter than human reaction times. Galileo's experiment was doomed by the limitation of human perception, but it established the crucial principle that light speed could be measured if sufficiently sensitive techniques were developed. The first successful measurement of light speed came from an unexpected source: astronomy. In 1676, Danish astronomer Ole Ragnar was studying the moons of Jupiter to create better navigation tables for ships. He noticed something peculiar about Io, Jupiter's innermost large moon. The timing of Io's eclipses behind Jupiter varied predictably depending on Earth's position in its orbit. Ragnar realized that when Earth was farther from Jupiter, Io's eclipses appeared to occur later than predicted. When Earth was closer to Jupiter, eclipses occurred earlier than expected. The only explanation was that light from Jupiter's system took measurably longer to reach. Earth when the distance was greater. Light had finite speed, and astronomical distances were large enough to detect travel time. Dr. Albert van Helden at Rice University has analyzed Rackhmer's original calculations and found them remarkably accurate given 17th century technology. Rackhmer estimated light speed at approximately 225,000 kilometers per second, about 25% slower than the actual value, but clearly demonstrating finite light speed for the first time in human history. The precision of light speed measurements improved dramatically with the development of terrestrial techniques that didn't rely on uncertain astronomical distances. In 1849, Hippolyte Vergeot created an ingenious apparatus using a rotating toothed wheel to chop light into brief pulses. By spinning the wheel fast enough, light passing through one gap would be blocked by the next tooth when it returned from a distant mirror. Vergeot's method required extraordinary precision in mechanical engineering and timing. The wheel had 720 teeth and was spun at rates exceeding 25 revolutions per second. Light traveled an 8.6-kilometer path between the wheel and a distant mirror. When the wheel rotated at precisely the right speed, returning light would be blocked by teeth that had moved into position during the light's travel time. This mechanical approach yielded light speed measurements accurate to within about 5% of the true value. A remarkable achievement using purely mechanical devices. Dr. Jed Buchwald at Caltech describes Vergeot's experiment as the first successful attempt to make light slow enough for mechanical devices to measure its speed. Leon Foucault improved on Vergeot's technique in 1850 by replacing the toothed wheel with a rotating mirror. As light traveled to a distant stationary mirror and back, the rotating mirror would turn slightly, deflecting the returning light beam. The amount of deflection was proportional to light speed, allowing more precise measurements than mechanical chopping methods. Foucault's rotating mirror technique could measure light speed over relatively short distances with unprecedented accuracy. His apparatus fit within a laboratory rather than requiring kilometers of open space. This development marked the transition from astronomical light speed measurement to controlled laboratory techniques that could be refined and repeated. The most precise 19th century measurements came from Albert Michelson, whose obsessive pursuit of light speed accuracy consumed decades of his career. Michelson developed increasingly sophisticated rotating mirror systems, culminating in measurements accurate to 0.02%, precision that wouldn't be significantly improved for nearly 50 years. Michelson's 1926 measurement between Mount Wilson and Mount San Antonio in California represented the pinnacle of classical light speed measurement. His apparatus used an octagonal rotating mirror system with precisely controlled rotation rates and carefully surveyed distances. The final value of 299,796,000 meters per second differed from modern values by only 0.001%. Extraordinary precision achieved with mechanical devices. Dr. Dorothy Michelson Livingston, Albert Michelson's daughter, documented how her father's pursuit of light speed precision bordered on obsession. Michelson would spend months adjusting mirror alignments and rotation speeds to eliminate sources of error measured in parts per million. His dedication to precision measurement established standards that influenced all subsequent experimental physics. The development of electronic timing methods in the mid-20th century revolutionized light speed measurement. Instead of mechanical rotating devices, scientists could use electronic circuits to create precisely timed light pulses and measure their travel times with accuracy limited only by the precision of electronic clocks rather than mechanical rotation rates. Dr. Keith Davy Froome at the National Physical Laboratory in England pioneered microwave techniques for measuring electromagnetic wave speeds in the 1950s. By measuring the frequency and wavelength of microwave radiation separately, then multiplying these values, Froome could determine light speed without directly timing light's travel over measured distances. These frequency wavelength multiplication techniques achieved unprecedented precision because they avoided cumulative errors associated with distance measurement and mechanical timing. Electronic frequency counters could measure electromagnetic frequencies to accuracies of 1 part in 1012, while interferometric techniques could measure wavelengths with similar precision. The combination of laser technology with atomic clocks in the 1970s pushed light speed measurement precision to extraordinary levels. Lasers provided highly coherent, monochromatic light sources ideal for interferometric measurement, while atomic clocks offered timing precision limited only by quantum mechanical uncertainties in atomic transition frequencies. Dr. Kenneth Evanson at the National Institute of Standards and Technology achieved the most precise light speed measurement in 1972 using helium neon lasers and cesium atomic clocks. This extraordinary precision revealed something unexpected. Measurements had become so accurate that uncertainties in the definition of the meter were limiting further improvement. The meter was defined as a specific fraction of Earth's circumference, but Earth's dimensions aren't perfectly stable. Tidal forces, geological processes, and measurement uncertainties created variations larger than the precision of light speed measurements. Scientists realized that light speed had become the most precisely measurable quantity in physics, more precisely known than the standard meter itself. This reversal of measurement hierarchy led to a revolutionary idea. Instead of measuring light speed in terms of predefined meters, why not define a meter in terms of precisely measured light speed? The decision to make light speed exactly 299,792,458 meters per second by redefining the meter represented a fundamental shift in measurement philosophy. Instead of treating light speed as a quantity to be measured, it became a defining constant that determines what we mean by distance and time measurements. Understanding the history of light speed measurement reveals how human ingenuity overcame seemingly impossible technical challenges. From Rivmer's astronomical observations to Michelson's mechanical precision to modern laser interferometry, each advance required revolutionary thinking about how to make the fastest phenomenon in nature slow enough for human technology to measure. This historical progression also illustrates how measurement precision drives scientific discovery. Each improvement in light speed measurement revealed new physics, from the finite nature of light propagation to relativistic effects to quantum limitations on measurement precision. The pursuit of measuring this cosmic constant ultimately transformed our understanding of space, time, and causality itself. Chapter 2. Redefinition Revolution in 1983. The international scientific community made one of the most radical decisions in the history of measurement. They stopped measuring the speed of light. Instead, they declared that light speed would be exactly 299,792,458 meters per second by definition, then redefined the meter to make this statement true. This wasn't scientific laziness or arbitrary decree. It was the logical conclusion of a measurement precision revolution that had made light speed the most accurately known quantity in all of physics. The problem that forced this redefinition was unprecedented in scientific history. Measurements had become more precise than the standards they were supposed to measure against. By the 1970s, scientists could measure light speed to within 4 parts per billion, but the official definition of the meter, based on the distance between 2 marks on a platinum iridium bar stored in Paris, was uncertain by about 4 parts in 10 million. Dr. Terry Quinn, former director of the International Bureau of Weights and Measures, describes this as the first time in history that a measurement became more precise than the standard it was measuring. The platinum iridium meter bar, carefully maintained at constant temperature and humidity, simply wasn't stable enough to support the precision that light speed measurements had achieved. The solution required reconceptualizing what measurement means at the most fundamental level. Instead of treating the meter as a fixed standard against which to measure light speed, scientists realized they should treat light speed as the fixed standard against which to define distance. This reversal transformed light speed from a measured quantity into a defining constant of reality itself. The redefinition process involved extraordinary international cooperation and scientific consensus. The General Conference on Weights and Measures, which had been refining measurement standards since 1875, needed to coordinate agreement among dozens of national measurement laboratories that had spent decades perfecting light speed measurement techniques. Dr. Barry Taylor at the National Institute of Standards and Technology led much of the technical work behind the redefinition. His team had to ensure that changing the definition of the meter wouldn't affect any practical measurements, while simultaneously enabling much higher precision in applications that depended on accurate distance and time measurements. The mathematics of redefinition was elegant in its simplicity. If light speed is defined to be exactly c equals 299,792,458 meters per second, and the second is independently defined by atomic clock standards, then the meter becomes defined as the distance light travels in exactly 1,299,792,458 of a second. This makes the meter a derived unit rather than a fundamental standard. This redefinition immediately solved a precision problem. Since atomic clocks can measure time intervals to better than 1 part in 1015, and light speed is exact by definition, distance measurements can now achieve precision limited only by the quality of atomic clocks and laser interferometry, rather than the stability of physical artifacts. The practical implementation required developing measurement techniques that could realize the new meter definition in working laboratories. The meter is now realized using laser interferometry. Scientists create electromagnetic standing waves using precisely frequency-controlled lasers, then measure distances in terms of the wavelength of these standing waves. Dr. John Hall at GELA pioneered many of the laser stabilization techniques that make modern meter realization possible. His work on optical frequency combs allows scientists to create laser light with frequency stable to better than 1 part in YOY, precision that would detect changes smaller than the diameter of a proton over laboratory-scale distances. The redefinition also had profound implications for how we understand the relationship between measurement and physical reality. By making light speed exact, scientists acknowledge that some aspects of nature are so fundamental that they define the framework within which all other measurements take place, rather than being measurements themselves. This philosophical shift reflects deeper insights about the nature of physical constants and their role in determining how the universe works. Light speed isn't just a property of electromagnetic radiation. It is the fundamental speed at which causality propagates through spacetime. Making this speed exact by definition recognizes its role as a structural feature of reality itself. The success of the light speed redefinition inspired similar approaches to other fundamental constants. The kilogram, long defined by a physical artifact called the International Prototype Kilogram, was redefined in 2019 based on Planck's constant, another fundamental constant that can be measured with extraordinary precision. Dr. David Newell at NIST led the effort to redefine the kilogram using quantum mechanical principles rather than physical artifacts. This redefinition completed the transformation of measurement standards from human-made objects to fundamental constants that reflect the deepest properties of nature. The meter redefinition enabled technological advances that would have been impossible under the old system. GPS satellites, which must account for relativistic effects to maintain accuracy, depend on precisely defined relationships between space and time that are only possible when light speed is exact rather than measured with uncertainty. Modern laser interferometry systems used in gravitational wave detection require distance measurements accurate to fractions of a proton diameter. LIGO's detection of gravitational waves was only possible because the meter definition allows such extraordinary precision in measuring tiny changes in the length of kilometer-scale laser beams. Dr. Rainer Weiss at MIT, Nobel laureate for his work on gravitational wave detection, credits the redefinition of the meter with enabling precision measurements that probe the fundamental structure of spacetime. Without exact light speed as a defining constant, Weiss explains, we couldn't measure gravitational wave effects that stretch space itself. The redefinition also resolved apparent contradictions that arose when different measurement techniques yielded slightly different values for light speed. These differences weren't due to physics changing, but to limitations in how distance standards were realized. Making light speed exact eliminated these discrepancies by making distance measurement dependent on light speed rather than independent of it. International acceptance of the redefinition required extensive verification that the new system would maintain continuity with previous measurements while enabling higher precision for future applications. National measurement laboratories around the world had to demonstrate that their laser-based meter realizations agreed with each other to better than the precision of the old platinum-iridium standard. The economic implications of higher precision measurement standards extend far beyond fundamental physics. Modern manufacturing, telecommunications, and navigation systems depend on precise distance and time measurements that are only possible because light speed provides an exact reference standard that never changes. Dr. Gerald Fraser at the National Physical Laboratory calculated that the economic benefit of higher precision measurement standards exceeds $100 billion annually in improved manufacturing tolerances, navigation accuracy, and telecommunications performance. The meter redefinition directly enables precision manufacturing at scales approaching atomic dimensions. The redefinition also eliminated a subtle but important source of confusion about the nature of scientific constants. Under the old system, light speed appeared to be a measured quantity that scientists were gradually determining with better precision. The new system makes clear that light speed is a defining feature of how space and time are related, not something that could in principle have different values. This distinction between measured quantities and defining constants reflects deeper questions about the relationship between mathematics and physics. Some quantities, like the ratio of a circle's circumference to its diameter, are mathematical constants that must have specific values in any self-consistent geometry. Light speed may be a similar type of constant that defines the geometry of spacetime itself. Modern physics increasingly treats fundamental constants not as arbitrary numbers that happen to characterize our universe, but as necessary features of any mathematically consistent physical reality. The exact value 299,792,458 isn't just a human choice about measurement units. It may reflect deep mathematical relationships that any universe with coherent space and time must satisfy. The meter redefinition thus represents more than just an improvement in measurement precision. It reflects humanity as growing understanding that the most fundamental aspects of reality are unmeasured quantities with defining principles that make measurement itself possible. Light speed doesn't just happen to have this exact value. This exact value defines what we mean by space, time, and causality. Understanding the redefinition revolution reveals that precision measurement isn't just about getting better numbers, but about discovering which aspects of nature are so fundamental that they define the framework within which all measurement takes place. The speed of light has become humanity's chosen reference point for understanding how the universe organizes space and time into a coherent, measurable reality. Chapter 3. Einstein's Revelation. When Albert Einstein published his special theory of relativity in 1905, he revealed that the speed of light isn't just the speed at which electromagnetic radiation travels. It's just the fundamental speed at which spacetime itself operates. This cosmic speed limit determines how quickly information can propagate through the universe, how space and time are unified into a single entity, and why nothing with mass can ever reach the speed of light. The number 299,792,458 represents far more than a measurement. It's the conversion factor between space and time built into the fabric of reality. Einstein's revolutionary insight emerged from a simple but profound observation. The speed of light appears to be the same for all observers, regardless of how fast they're moving. This contradicted common sense and classical physics, which predicted that light speed should vary depending on the observer's motion, just like the speed of sound varies depending on whether you're moving toward or away from the source. Dr. Gerald Holton at Harvard University has studied Einstein's thought processes leading to relativity theory. Einstein realized that if light speed is truly constant for all observers, then space and time themselves must be flexible rather than absolute. What we experience as space and time are really projections of a unified four-dimensional spacetime onto our three-dimensional perception. The mathematical framework of special relativity reveals that space and time are related by exactly the factor c, the speed of light squared. This means that space and time are different aspects of the same underlying reality, connected by the fundamental conversion constant 299,792,458 meters per second. Energy and mass are related by this same conversion factor in Einstein's famous equation E equals mc. This unification explains why light speed has such a precise, specific value rather than being arbitrary. The speed of light is really the speed of spacetime, the rate at which cause and effect can propagate through the universe. It's not primarily about electromagnetic phenomena, but about the fundamental structure of reality itself. Einstein's analysis revealed that 299,792,458 meters per second represents the speed at which massless particles must travel through spacetime. Photons, which carry electromagnetic radiation, travel at this speed not because they're special, but because they have no mass to slow them down. Any massless particle, including gravitons that carry gravitational waves, must travel at exactly this speed. Dr. Kip Thorne at Caltech explains that spacetime geometry requires this speed limit. The speed of light is really the speed of spacetime geometry. It's the rate at which the curvature of space and time can change and propagate. This speed isn't arbitrary. It's determined by how space and time fit together into a unified structure. The constancy of light speed for all observers leads to extraordinary consequences that challenge everyday intuition. Time dilation means that rapidly moving clocks run slower relative to stationary observers. Length contraction means that rapidly moving objects appear shorter in the direction of motion. These effects become significant only at speeds approaching the speed of light. At everyday speeds, relativistic effects are negligible because 299,792,458 meters per second is so much faster than normal motion. A car traveling 100 kilometers per hour moves at only 0.00000000009% of light speed, making relativistic correction smaller than 1 part in Ya. But as speeds approach light speed, these effects become dominant and ultimately prevent massive objects from reaching or exceeding this cosmic speed limit. The mathematical structure of relativity shows why exceeding light speed is impossible for massive objects. As an object's speed increases toward light speed, its relativistic mass increases toward infinity, requiring infinite energy to accelerate it further. The speed of light represents an asymptotic limit that massive objects can approach but never reach. This speed limit isn't arbitrary, but emerges from the geometric structure of spacetime itself. Dr. Brian Greene at Columbia University describes it as the speed at which the universe processes information, the rate at which cause and effect can propagate through the cosmic information network. Einstein's revelation also explains why electromagnetic radiation travels at this specific speed. Maxwell's equations, which describe electromagnetic phenomena, contain a combination of electric and magnetic constants whose ratio determines electromagnetic wave speed. This speed equals the fundamental spacetime speed because electromagnetic fields are disturbances in spacetime itself. The unification of space and time through the speed of light resolves classical puzzles about electromagnetic radiation. Why do electromagnetic waves travel through empty space without requiring a medium? Because they're disturbances in spacetime geometry rather than waves in a substantial medium. The medium is the geometric structure of space and time. Modern experimental physics has confirmed Einstein's predictions with extraordinary precision. Particle accelerators routinely accelerate electrons and protons to speeds exceeding 99.99% of light speed, confirming that relativistic mass increase prevents reaching or exceeding the speed of light. The energy required for further acceleration increases so rapidly that no finite energy source can push massive particles beyond this limit. GPS satellites provide everyday confirmation of relativistic effects caused by the fundamental speed of light. These satellites experience both special relativistic effects due to their motion and general relativistic effects due to weaker gravitational fields at their altitude. Without relativistic corrections, GPS accuracy would degrade by several kilometers per day. Dr. Neil Ashby at the University of Colorado has calculated the precise relativistic corrections required for GPS accuracy. Special relativity causes satellite clocks to run slower by about 7 microseconds per day due to their high orbital speeds. General relativity causes them to run faster by about 45 microseconds per day due to weaker gravity. The net effect must be corrected to maintain GPS precision. The speed of light is spacetime speed also explains why information cannot travel faster than light. Information propagation requires cause and effect relationships, which are limited by the speed at which spacetime geometry can change. Faster-than-light information transfer would violate causality by allowing effects to precede their causes. Quantum entanglement, while appearing to involve instantaneous correlations between distant particles, doesn't violate the light speed limit because it cannot transmit information. The correlations predicted by quantum mechanics are statistical and cannot be used to send messages faster than light. Einstein's speed limit for information transfer remains inviolate. The discovery of gravitational waves by LIGO confirmed that gravitational disturbances also travel at exactly the speed of light. When two black holes merge, the gravitational waves they create propagate through space at 299,792,458 meters per second, just like electromagnetic radiation. This confirms that both phenomena involve disturbances in spacetime geometry traveling at the fundamental spacetime speed. Dr. Gabriela Gonzalez, former spokesperson for the LIGO scientific collaboration, describes gravitational wave detection as seeing spacetime itself vibrate at the speed of light. We're detecting ripples in the fabric of reality propagating at the fundamental speed that Einstein predicted. The profound implications extend beyond physics to philosophy and cosmology. If spacetime has a fundamental speed limit, then the universe has an intrinsic temporal structure that determines how events can be causally connected. The light cone structure of relativity defines which events can influence each other and which cannot. This temporal structure may explain why the universe appears to have a consistent arrow of time and why causality flows from past to future rather than randomly in all temporal directions. The speed of light creates a framework within which coherent physical processes can unfold without logical contradictions. Einstein's revelation about light speed also connects to quantum mechanics through the uncertainty principle. The precise value 299,792,458 meters per second may reflect fundamental quantum limitations on how precisely space and time can be defined simultaneously. The conversion between space and time may involve quantum mechanical uncertainties that determine this specific speed. Modern theories of quantum gravity suggest that spacetime itself may have quantum mechanical properties at the Planck scale. Distances so small that quantum uncertainty makes the classical concept of spacetime geometry break down. The speed of light may represent the classical limit of more fundamental quantum processes that operate below the scale of measurement. Understanding Einstein's revelation transforms how we interpret the precise value 299,792,458 meters per second. This isn't just a measurement of how fast light travels. It is a fundamental constant that defines how space and time are unified, how causality propagates through reality, and how information can flow through the cosmic network of cause and effect. The speed of light represents humanity's most direct measurement of the speed at which the universe itself operates. Every photon that enters your eyes has traveled at exactly this speed, because this is the speed at which spacetime processes the information carried by electromagnetic disturbances. Chapter 4. Fundamental Constants. The speed of light doesn't exist in isolation, but forms part of an intricate web of fundamental constants that together determine how the universe operates at the most basic level. The precise value, 299,792,458 meters per second, is intimately connected to other universal constants, including Planck's constant, the fine structure constant, and the permeability of free space. These relationships reveal that light speed isn't an arbitrary number, but emerges from the mathematical structure underlying all physical reality. In Maxwell's electromagnetic theory, the speed of light emerges from two more fundamental constants: the electric permittivity of free space, epsilon eb, and the magnetic permeability of free space, mu eb. Light speed equals exactly 1 square root epsilon mu, showing that electromagnetic wave propagation depends on how strongly empty space itself responds to electric and magnetic fields. Dr. Frank Wilczek at MIT describes these constants as the electromagnetic personality of empty space. The permittivity determines how strongly electric fields can exist in vacuum, while permeability determines how strongly magnetic fields can exist. Their combination determines the impedance of free space, its resistance to electromagnetic wave propagation. The numerical value of light speed in meters per second depends on human choices about measurement units, but the dimensionless combinations of fundamental constants reveal deeper truths about nature. This dimensionless constant appears throughout atomic physics, determining everything from atomic sizes to the energy levels of hydrogen atoms. The fact that alpha approximately equals 137th rather than some dramatically different number may be necessary for the existence of stable atoms and chemistry. If alpha were much larger, electrons would spiral into nuclei. If much smaller, atoms would be too large and weakly bound to form stable matter. Dr. John Barrow at Cambridge University has explored how the fundamental constants determine the structure of possible universes. In his analysis, the speed of light appears not as an isolated constant, but as part of a mathematical framework that must be internally consistent for any universe to support complex structure and coherent physical processes. Planck's constant A, which determines the scale of quantum mechanical effects, is related to light speed through the Planck length L, p equals square root ag per c cubed, and Planck time t, p equals square root ggc. These Planck units represent natural scales where quantum gravitational effects become important, suggesting that light speed may be determined by quantum properties of spacetime itself. The Planck length, approximately 10 meters, represents the smallest distance that has meaning in physics. Below this scale, quantum fluctuations in spacetime geometry become so large that classical concepts of distance and time break down. The speed of light connects this quantum scale to macroscopic physics through fundamental geometric relationships. Einstein's mass-energy relation E=mc shows how light speed connects matter to energy through the conversion factor c². This relationship isn't limited to nuclear physics, but applies to all forms of energy and mass. Even the mass of everyday objects reflects energy content divided by c², showing that light speed determines the exchange rate between matter and energy throughout the universe. Dr. Lisa Randall at Harvard University points out that c represents the cosmic exchange rate between space and time, matter and energy. This exchange rate must have exactly the right value to allow stable matter, coherent chemical processes, and ultimately the complex structures needed for life and intelligence. The gravitational constant g combines with light speed to determine fundamental scales in cosmology. The Schwarzschild radius of a black hole, Rs equals 2gm per c², shows how light speed determines the boundary at which gravitational fields become so strong that not even light can escape. This connects light speed to the most extreme gravitational phenomena in the universe. Cosmological models reveal that light speed, combined with other fundamental constants, determines the overall structure and evolution of the universe. The critical density for cosmic expansion depends on combinations of g, c, and the Hubble constant, showing that light speed helps determine whether the universe will expand forever or eventually collapse. The relationship between fundamental constants also appears in particle physics through dimensional analysis. Dr. Steven Weinberg's work on the cosmological constant problem reveals deep connections between light speed and vacuum energy. The energy density of empty space, if calculated naively from quantum field theory, would create gravitational effects that make stable cosmic expansion impossible. The resolution may involve relationships between light speed and other constants that we don't yet understand. Modern attempts to unify fundamental forces suggest that light speed may not be truly fundamental, but might emerge from more basic principles in theories of quantum gravity. String theory, loop quantum gravity, and other approaches propose that c, and g might all be emergent properties of more fundamental discrete structures at the Planck scale. The anthropic principle suggests that the values of fundamental constants, including light speed, must be compatible with the existence of observers who can measure them. If light speed were significantly different, stable atoms might be impossible. Stellar evolution might not produce heavy elements, or cosmic expansion might prevent galaxy formation. Dr. Martin Rees at Cambridge University has identified several cosmic coincidences involving fundamental constants that seem necessary for complex structure formation. The ratio of electromagnetic to gravitational force strengths, determined partly by light speed, must fall within narrow ranges to allow star formation, nucleosynthesis, and planetary development. Precision tests of whether fundamental constants actually remain constant over cosmic time have focused particularly on possible variations in light speed. Observations of distant quasars and ancient cosmic microwave background radiation can detect whether Ca or other dimensionless combinations have changed over billions of years. Dr. John Webb at the University of New South Wales has conducted some of the most precise searches for varying constants using absorption lines in quasar spectra. His results suggest possible tiny variations in the fine structure constant over cosmic time, which would imply changes in the relationships between fundamental constants, including light speed. The possibility of varying constants raises profound questions about the nature of physical law. If fundamental constants can change, then the mathematical relationships that define physical reality might themselves evolve over cosmic time. Light speed might not be eternal, but could represent a temporary configuration of deeper principles we have discovered. Quantum field theory reveals that even empty space has structure related to fundamental constants. The vacuum energy density and the rates of virtual particle creation depend on combinations of c and other constants. These quantum vacuum properties may determine why light speed has its specific value rather than some other number. The renormalization procedures required to make quantum field theory mathematically consistent involve relationships between fundamental constants that must satisfy specific constraints. These mathematical requirements may explain why nature's constants have their observed values. They may be the only values consistent with mathematically coherent quantum field theories. Modern precision measurements of fundamental constants reveal correlations and constraints that weren't apparent when the constants were measured individually with lower precision. The speed of light is now known so precisely that its relationships with other constants can be tested to unprecedented accuracy, revealing subtle effects that may point toward deeper underlying principles. Understanding light speed as part of the web of fundamental constants reveals that 299,792,458 meters per second isn't an isolated fact about electromagnetic radiation. It's part of a mathematical structure that may determine the very possibility of coherent physical reality, stable matter, and complex structures capable of evolution and consciousness. The precision with which we know this speed reflects humanity's growing ability to probe the mathematical foundations of existence itself. Each improvement in measurement accuracy reveals new aspects of how fundamental constants interconnect to create the rich, structured universe we inhabit and study. Chapter 5. Measurement Precision. The measurement of light speed to the exact value, 299,792,458 meters per second, represents one of the most extraordinary achievements in experimental physics. A triumph of human ingenuity over the fundamental limitations imposed by the speed of the phenomenon being measured. Reaching this precision required revolutionary advances in atomic clocks, laser stabilization, interferometry, and quantum metrology that pushed measurement science to its theoretical limits and beyond. The challenge of measuring light speed with extreme precision is fundamentally different from measuring slower phenomena. Light travels so fast that it can cross the diameter of a human hair in less than a femtosecond, a unit of time so brief that there are more femtoseconds in 1 second than there are seconds in 30 million years. Measuring such rapid motion requires timing techniques that approach quantum mechanical limits of precision. Dr. John Hall at Gila pioneered the laser frequency comb technique that made ultra-precise light speed measurement possible. His invention allows scientists to measure optical frequencies with the same precision as radio frequencies, effectively creating a gear system that connects the rapid oscillations of laser light to the slower oscillations that atomic clocks can measure directly. Frequency combs work by using mode-locked lasers that emit extremely short pulses of light containing millions of precisely spaced frequency components. The spacing between these frequency components can be measured with extraordinary precision, allowing the absolute frequency of laser light to be determined with uncertainty smaller than 1 part in 1017. Precision that would detect frequency changes smaller than 1 cycle per year in laser light oscillating at 500 trillion cycles per second. This level of precision required solving technical challenges that seemed impossible just decades earlier. Laser light frequencies are so high that no electronic device can directly count optical oscillations. The frequency comb technique effectively slows down optical frequencies through nonlinear optical processes that preserve phase relationships while creating measurable beat frequencies between different laser modes. Dr. Theodor Hensch at the Max Planck Institute shared the 2005 Nobel Prize for developing frequency comb technology. His work revealed that ultra-short laser pulses naturally contain the frequency relationships needed for precision measurement, but only if the laser pulse timing and frequency stability could be controlled with unprecedented accuracy. Modern atomic clocks provide the foundation for extreme precision in light speed measurement. The current definition of the second is based on cesium atomic transitions that oscillate at exactly 9,192,631,770 cycles per second. This frequency is known so precisely that cesium clocks can measure time intervals with uncertainties smaller than 1 part in 1016, equivalent to gaining or losing less than 1 second over 300 million years. The most advanced atomic clocks now use optical transitions in single-trapped ions or neutral atoms that oscillate at frequencies hundreds of thousands of times higher than cesium transitions. These optical atomic clocks achieve fractional frequency uncertainties approaching 1019, making them sensitive to gravitational time dilation effects caused by elevation changes of just a few centimeters. Dr. Andrew Ludlow at NIST leads research on optical atomic clocks that may redefine timekeeping standards within the next decade. His strontium lattice clocks can detect frequency changes so small they would be affected by the gravitational field differences between your head and feet, demonstrating precision that pushes against fundamental quantum mechanical limits. The combination of frequency combs and optical atomic clocks allows light speed to be measured by determining both the frequency and wavelength of laser radiation with extraordinary precision, then multiplying these values to obtain C equals lambda nu. This approach avoids the timing uncertainties that limited earlier direct time-of-flight measurements. Laser stabilization techniques developed for precision light speed measurement have achieved frequency stabilities that challenge theoretical limits imposed by quantum mechanical fluctuations. The most stable lasers are locked to ultra-high finesse optical cavities whose length changes are controlled to fractions of an atomic radius, creating frequency references more stable than any natural atomic transition. Dr. Jundi at Gila has developed laser systems stable enough to detect frequency changes that would result from moving the laser apparatus by distances smaller than the radius of a proton. These systems use sophisticated vibration isolation, temperature control, and magnetic shielding to eliminate environmental perturbations that could affect laser frequency by even infinitesimal amounts. The measurement precision achieved in determining light speed now exceeds the stability of the most carefully controlled physical standards. Variations in Earth's rotation, tidal effects on laboratory dimensions, and thermal expansion of measurement apparatus introduce uncertainties larger than the precision with which light speed itself can be measured. This precision revolution required developing new statistical and systematic error analysis techniques. When measurement uncertainties become smaller than many of the effects being studied, experimenters must account for previously negligible systematic errors, including relativistic corrections, quantum mechanical uncertainties, and gravitational effects that were irrelevant in less precise experiments. Dr. Barry Taylor at NIST developed much of the mathematical framework for analyzing ultra-precise measurements where classical error analysis techniques break down. His work ensures that claimed measurement uncertainties accurately reflect the true precision limits imposed by both known systematic effects and fundamental quantum mechanical principles. The realization that light speed measurements had become more precise than the definition of the meter led to the revolutionary decision to make light speed exact by definition. This represented the first time in scientific history that a measured quantity became so precisely known that it was promoted to the status of a defining constant. Modern implementations of the meter definition using laser interferometry can realize the meter with uncertainties approaching 1 part in 1017, precision that would detect length changes smaller than the diameter of a proton over kilometer-scale distances. This extraordinary precision enables applications in gravitational wave detection, precision manufacturing, and tests of fundamental physics. The technological spin-offs from ultra-precise light speed measurement have transformed multiple fields of science and engineering. GPS technology depends on relativistic corrections that require precise knowledge of light speed relationships. Precision manufacturing uses laser interferometry techniques developed for metrology. Optical communications relies on frequency stabilization methods pioneered for fundamental measurements. Dr. Fritz Riehel at the Physikalisch-Technische Bundesanstalt has calculated that the economic impact of precision metrology, enabled by ultra-precise light speed, knowledge exceeds $100 billion annually in improved manufacturing, navigation, telecommunications, and scientific instrumentation. The techniques developed to measure this one fundamental constant have revolutionized humanity's ability to measure and control physical phenomena. Current research pushes measurement precision toward fundamental quantum limits where the measurement process itself affects the quantity being measured. Heisenberg's uncertainty principle may ultimately limit how precisely light speed can be known relative to other quantities, creating fundamental trade-offs between precision and different physical measurements. Future developments in quantum sensing and entangled atomic clocks may enable even higher precision measurements that probe whether fundamental constants remain truly constant over time. Networks of ultra-precise atomic clocks distributed across Earth and in space could detect minute variations in light speed or other constants that might reveal new physics beyond current theories. Dr. Mariana Safronova at the University of Delaware leads theoretical work on using precision atomic measurements to search for dark matter interactions, fifth forces, and other phenomena beyond the standard model of physics. These searches require measurement precision approaching the theoretical limits imposed by quantum mechanics itself. The pursuit of measurement precision in determining light speed also revealed fundamental limitations of classical measurement concepts. Quantum mechanics shows that all measurements involve interactions between measuring apparatus and measured systems that introduce irreducible uncertainties. Understanding these quantum measurement limits has profound implications for the foundations of physics. The extraordinary precision achieved in measuring light speed demonstrates humanity's growing mastery over the quantum mechanical tools needed to probe nature's fundamental structure. Each improvement in measurement technique reveals new layers of physical reality while approaching the ultimate limits imposed by the quantum mechanical foundations of measurement itself. The exact value, 299,792,458 meters per second, thus represents not just a number, but the culmination of centuries of scientific and technological development that has brought human measurement capability to the edge of what quantum mechanics permits. This precision achievement opens new frontiers in fundamental physics, while providing the technological foundation for increasingly sophisticated applications that depend on ultra-precise knowledge of how space, time, and light interact in the quantum world.